A lovely cat.
Yes, that's the idea.
Okay, great.
Okay,
Okay.
very good. So shall we go?
Yes.
All right. So thanks for being here listening to me. I have many pleasant memories of the MIT experience. I was a grad student at Harvard myself, but I took my most fun classes at MIT. I took GR and cosmology and particle physics. And then I was a postdoc at MIT for 3 years. So I spent a lot of time on the infinite corridor, et cetera. And I'm here coming back virtually to tell you about quantum mechanics. So we have a lot to cover, so let's just get into it. For the purposes of this chat, what I really want to emphasize is the conceptual shift that you should try to undergo when you think about the difference between classical mechanics and quantum mechanics. If you take a class at MIT on quantum mechanics, maybe not from Seth or Michelle, I don't know, but from the typical physics professor, most of your time will be spent solving the Schrodinger equation. You have a differential equation, you can solve it. There are polynomials involved. There are WKB approximations and perturbation theory, and it's all just applied partial differential equations. And that kind of hides the fact that, at least implicitly in quantum mechanics, there is a truly revolutionary view of the universe. So to get that in our brains, let's think about the ordinary view of the universe, which is stuff arranged in space. So here I have a picture of a very small part of the universe. There's a chair in a room, there's a floor and some curtains. And we think if you want to describe the world, if you're taking your classical physics class, you would have three-dimensional space. You have objects arranged in it. Those objects would have positions and velocities, and you would talk about what's going on. So the quantum mechanical motto, I claim, is that what we see when we look at the universe is not all that there is. In fact, that reality is a superposition of many different versions of this story of things arranged in space. And I'm not yet being fancy about many worlds, as we'll talk about in great detail. This is just standard quantum mechanics. The way that we describe the world vis-a-vis, in comparison to the classical way of describing the world, is as a superposition of multiple possibilities all at once. And the more radical claim is that reality can be divided up into these individual worlds, each of which looks like stuff arranged in space. So these are true parallel universes, is the idea. To get there, I wanted to get you there slowly, because it's not like some physicists sat around and were having something to drink and said, like, dude, wouldn't it be awesome if there were all these different worlds? Okay. It's very much a tortuous journey that physics went on, pushed by the need to account for the data. So think about what life was like for physics in the 19th century, right? We had classical mechanics as an overarching paradigm that was given to us by Newton. And the basic way you do physics is you say you have a state of the physical system. So in classical mechanics, that's the position and velocity, or position and momentum of every object. So that's a point in phase space. And then you have some equations of motion, F equals ma, and F equals the inverse square law for gravity. And then you solve those differential equations and you get motion. So it wasn't until Pierre-Simon Laplace, much later, circa the year 1800, Newton was in the 1600s. In 1800, Laplace points out the real deep philosophical implications of this idea. The Laplace's demon thought experiment says if you had a vast intelligence, which Laplace himself never called a demon, these days we would call it a computer, of course, that had perfect knowledge of the world. So perfect knowledge of the position and velocity of every particle in the world, and perfect knowledge of the laws of physics, and the ability to compute infinitely accurately, then to that vast intelligence, the future and past would be entirely fixed, entirely known. There's no mystery in the whole history of the universe. The present state of reality tells you what's going to happen next with perfect deterministic fidelity. Quantum mechanics is going to come along, and to give away the secret, it's that what we observe about the universe is much less than what actually exists. And that means that we're bringing the word observe into physics for the first time. Of course, you were allowed to observe things in the classical world, but there was nothing tricky about it. You just went out and observed things. You observed what was, right? If Isaac Newton says the planets in the solar system have certain positions and velocity, you just go out and observe them. Quantum mechanics, as we will see, says something very different. So why did we get there? And usually the story goes back to 1900 and Planck and Einstein with radiation. But I think it makes more conceptual sense to start a little bit later. Ernest Rutherford, in the first decade of the 20th century, was trying to figure out the structure of atoms. And he came up with this model, which is still the cartoon that we use to represent physics or science today. The Rutherford atom has a nucleus, which is a heavy, positively charged thing. And orbiting the nucleus are electrons, which are very low mass, negatively charged things. This is a beautiful thing. It kind of resembles the solar system a little bit. It's easy to picture. It makes some predictions that do okay, some others that don't do so well. It makes one prediction that does really, really, really badly. Because if you have an electron, that's a charged particle. A charged particle moving in a circle will give off electromagnetic radiation, right? If you take an electron and you shake it or you move it in a circle, there are electromagnetic waves that move out at the speed of light, depending on the frequency of your oscillations. That means that these electrons don't just sit there in the same orbits forever. They lose energy, which means they spiral in to the center of the atom where the nucleus is. You can even calculate. It's a nice little homework assignment. Calculate typically how long would it take for an electron to lose enough energy to spiral all the way into the nucleus. The answer is about 10 to the minus 11 seconds. So we can do that experiment. There, we did it. It didn't happen. Atoms are stable. You and I are made of atoms. Our atoms clearly last for longer than 100th of a billionth of a second. This theory is clearly wrong. What's going on? So there were some steps. We're going to skip some steps. A big step toward getting the right answer happened in 1924 when Louis de Broglie, who was a graduate student at the time, this is a little challenge to you graduate students out there. What are you going to do with your PhD thesis? Louis de Broglie's PhD thesis was suggesting that electrons should be thought of as waves rather than particles. So we would call this wave today the wave function of the electron. And we would, an example of it would be if you've ever taken a chemistry class and you've learned about the orbitals that electrons have in different kinds of atoms. You see that these are wave-like shapes. They're definite shapes with, discrete possible places that they can take. That's because they're particular shapes of definite energy. But what it means is there's a minimum size for the wave to take around the electron, around the nucleus rather. And this is supposed to explain the stability of matter. The electron is not, in this view, a particle moving in an orbit. It's not even a particle moving randomly in a cloud. In this view, the view that I'm going to advocate, although not everyone agrees with it, the electron is the cloud. That is what the electron is. And so you ask the question, what is the shape of the cloud? And for all of these orbitals, the shape of the cloud is constant in time. There's no vibration going on. There's no orbiting going on. So there's no reason to emit electromagnetic waves and decay. And very soon thereafter, Erwin Schrödinger suggests that he can come up with an equation that these waves satisfy. It's a little bit more sophisticated than de Broglie's point of view, because in Schrödinger's picture, the wave function is a complex valued function. So at every point in space, there's a complex number. We call this psi of x, the wave function. And he gives us an equation, and you can solve that equation, and you can actually find all of these orbitals that we just saw. So you don't need to sort of posit various things. You have a differential equation. This makes scientists very happy. Physicists love differential equations. They know how to solve them. There's also a version of quantum mechanics from Heisenberg and his collaborators that used matrices. Physicists didn't like that. They didn't know how to use matrices at the time, but differential equations they knew all about ever since Maxwell, right? So this is extremely successful. Schrödinger became famous for doing this, as well as for doing other things. It was a full employment kind of thing for physicists. You can solve the Schrödinger equation to your heart's content. To this day, as I mentioned, most of your time, if you take a quantum mechanics course, will be spent solving this wave equation. The problem is, when you look at electrons, you don't see waves. You see particles. This is a little video of a radioactive source. So I think it's a little bit of radium or something like that. So these are not electrons coming out, but they're particles coming out. And if you look at the Schrodinger equation, we're not going to do it, but if you asked what the prediction is for the wave function of a particle that is being emitted by a radioactive source, that wave function comes out in a spherical pattern. It's a wave that is equally strong in every direction. So maybe you would expect when you look at a decaying nucleus or something like that, and it decays, you see a big puffy cloud, but you don't. This is the source in a cloud chamber, and you see these lines. These lines are the trajectories of particles that are being emitted by the radioactive source. They look exactly like particles. This is what particles look like. They have a position, it's changing over time. Their trajectory is a line, okay? That's a puzzle. This is the birth of the puzzle that we're still wrestling with 100 years later. It is almost as if electrons behave like waves, but only when we're not looking at them. And as soon as you look at them, as soon as you measure them or observe them, they start looking like particles. Now, this is obviously crazy talk, right? Like, how does the electron know if I'm looking at it? Why should looking or observing have anything to do with the most fundamental laws of nature? So we did what we always do in science. We assembled the greatest minds we could find. So in 1927, we had the fifth Solvay Conference, which brought together, you can see here, Einstein and Planck and Marie Curie, also Bohr and Heisenberg and de Broglie and Schrodinger and Pauli, and everyone who was everyone in quantum physics. They got their heads together in Brussels. They drank some good Belgian ale, and they came out a few days later and said, okay, we have it figured out. Here's what's happening. Indeed, electrons are waves when you don't look at them, and they are particles when you do look at them. That is the solution. So specifically, they invented something called collapse of the wave function. So the idea is that, again, when you're not looking at it and you just solve the Schrodinger equation, the electron has a wave function. It has a certain shape. But then you say, I measured the position. The position of the electron is something I'm allowed to measure. It's something we call an observable of the system. And when you measure an observable, you get an answer. You don't get an ambiguous set of possibilities. You say, here is the electron. So the jargon that we invented is the wave function of the system has spontaneously collapsed when it was observed from spread out in some shape like an orbital or whatever to some specific location, highly, highly localized at that particular location. We can't tell you exactly where it will be localized to. This process is intrinsically indeterministic. It undermines Laplace's dream, or Laplace's demon's dream anyway, of exactly knowing the future of the universe based on its present state. And so what we teach our students still today in quantum mechanics courses is a set of two different rules. There's one set of rules in quantum mechanics that applies when you're not measuring a system. And those rules are very simple. Those rules exactly match on to just a very slight variation on classical physics. The rules are you have a state and it evolves according to some differential equation. The difference is, of course, that the state in classical mechanics would have been positions and momenta of all the different particles. Now, the state is defined by this wave function thing. A wave function just depends on all the positions of all the particles all at once. But still, it's a thing. It's a state. It's a mathematical object. And then we have an equation that tells you how that mathematical object evolves over time. It's the Schrodinger equation. If that was all there were to quantum mechanics, you would think that it wouldn't be that revolutionary. It would be just kind of like classical mechanics. But then, in order to explain what you see in the lab, they had to invent these other rules that kick in when the system is measured. When the system is measured, the wave function collapses, and you can't exactly predict where it will collapse. There's a rule relating the value of the wave function to the probability of seeing different possible measurement outcomes. That rule is called the Born rule, after Max Born, who's a different pioneer of quantum mechanics than Niels Bohr, even though their names look similar. And the Born rule is that the probability is given by the absolute value of the wave function squared. And he won the Nobel Prize for that. Until recently, this was the last time, the Born rule was the last time that a Nobel Prize had been given for work in the foundations of quantum mechanics. So this set of rules, the rules for what happens when you don't measure and when you do, together constitute the textbook or Copenhagen interpretation. This is what we teach our students. The problem with that view is that it's clearly wrong. It is clearly unacceptable, or at least incomplete. This is supposed to be the way that nature works at the fundamental level. This is what we scientists are trying to get our heads around, how reality itself plays out, okay? And these rules that I gave you right here are clearly not that. Why are they? Because they don't answer certain questions. If you're telling me that you have a theory of the world, and it's the most fundamental theory you have, then it could be right or wrong, but it should certainly be well defined. It should certainly answer whatever questions you want to ask of it, and this theory does not do that. So there are two major problems in this theory that we still are arguing about today. There is what we call the measurement problem. This is just, what do you mean when you say measure or observe or something like that, right? Like this word had never appeared in fundamental theories of physics before, and now there it is, right in the axioms of your theory. What counts as a measurement? When does it happen? Who is allowed to do it? Do I need a PhD to do the measurement? Could I be a cat or an earthworm? What if I just glance at it a little bit? Could a robot do it? Okay, is somehow consciousness or human agency involved in this? We don't know the answer to any of these questions. There are very grown-up working physicists who have very different answers to these questions. They might individually insist that their answers are right, but the rest of the community does not agree with them, so we don't know what the answer is. That's far too vague to be part of a fundamental theory of physics. The other problem is the reality problem. Our goal in physics, in science, is to describe the real world, to understand what is going on in the real world. Now, you've told me there's something called the wave function of the electron, but it's not what I observe. So, okay, what is it? Is reality represented by a wave function? If it is it the entire representation of reality, or are there other things in addition to the wave function? Or is it not involved with reality at all? Is the wave function simply a tool that we use to make predictions? Maybe what matters, what's real, is the experimental outcomes, and the wave function is just a subjective thing that different people can have opinions about, okay? That's all fine, but again, grown-up physicists disagree with these questions, and that means we don't understand quantum mechanics, even though it's almost 100 years old. So there are plausible solutions. This is something I want to emphasize. It's not that it's so mysterious that we're stuck and we'll never get the right answer. The problem is we don't agree on what the answers are. So back in the bad old days of early quantum mechanics, we would have talked about competing interpretations of quantum mechanics, and sometimes people still talk that way. But it's not exactly right. These days, we actually have legitimately distinct scientific theories, some of which even are experimentally testable. So let me tell you what some of those are. We're going to focus in on one, but I'll give you the broad roadmap here first. So you can think of it as a flow chart, right? You can first ask yourself, does quantum mechanics describe reality directly, or is it only about making predictions for observations? If it's just about making predictions, then we have what we call epistemic theories. In other words, the wave function is just a tool to summarize the knowledge that we have about a system. If that's not right, if the wave function is supposed to represent reality, then we ask, is it only the wave function? Is the wave function the entire story, or are there other physical quantities as well? If there are other physical quantities, then we have what are called hidden variable theories. This is basically what Louis de Broglie had in mind back in the day. He didn't quite ever finish explaining his theory, but he kind of thought that an electron had both a particle-like aspect and a wave-like aspect, and you would have to include them both. But that kind of fell out of favor. Most physicists these days go on the lines that it's just the wave function out there. And then you have to ask, what does the wave function do? Does it always obey the Schrodinger equation? Or does it collapse sometimes? And if it collapses, does it collapse all by itself randomly? Or does it collapse because you did something to it or something like that? If it collapses, then we have what are called objective collapse theories. And if it never collapses, if it just always obeys the Schrodinger equation, then we get the Everettian theory of quantum mechanics, or the many worlds theory. That's what we want to focus on today. But before we go into many worlds, there's one more anecdote that I have to tell you, because it really illustrates the sad state of physics research in the foundations of quantum mechanics today. I said that Max Born won the Nobel Prize for foundations of quantum mechanics back in the 50s. Of course, many people won it before him, but then there was a long gap. And then there was another Nobel Prize that was just given out a few years ago for work in the foundations of quantum mechanics to Ospe, Clauser, and Zeilinger. They tested something called the Bell inequalities. John Stuart Bell invented these inequalities that are supposed to distinguish quantum theories from classical theories. And of course, the Nobel Committee comes out with a press release. And in the press release, they said the following: John Stuart Bell developed a mathematical inequality that is named after him, which states that if there are hidden variables, the correlation between the results of a large number of measurements will never exceed a certain value. However, quantum mechanics predicts that a stronger type of experiment will violate Bell's inequality. That's wrong. That is not what the Bell theorem says, because they left out a crucial word where they say here, if there are hidden variables, you can't match the predictions of quantum mechanics. That's not right. What Bell, in fact, indeed, Bell believed in hidden variables. His favorite model of quantum mechanics featured hidden variables. What the theorem actually talks about are models with local hidden variables. That is to say, hidden variables that are localized to points in space and only interact locally from one place to another. In what are called pilot wave theories or de Broglie-Bohm theories, there are hidden variables, but they don't behave locally, and they can perfectly match the predictions of Bell's theorem. Even the people who give out the Nobel Prize did not quite wrap their heads around that, which is kind of depressing. But I don't think that's the right theory anyway. I just want to, stand up for it a little bit. I want to give you the sales pitch for that last option that we talked about, the many worlds interpretation of quantum mechanics. And I know that we haven't gotten there yet, but I really want to go through all these steps to emphasize that many worlds wasn't just invented for fun. There was a good reason, a good chain of logic that gets you there. The first step is, I think, to me, there's very good reason to take the wave function seriously as a physical, real object. That is to say, not simply as a way to organize our knowledge, not simply as something we use to calculate a probability distribution. Probability distributions are easy, right? Like many of the founders of quantum mechanics, including people like Einstein, thought that ultimately quantum mechanics would be understood in ways similar to statistical mechanics. There's something true about the world, but we don't know what it is, so we assign a probability distribution, and maybe the wave function helps us do that. The problem is things like the famous double slit experiment. You send a wave function through two slits, you detect what it gives you on a detecting screen on the opposite side. Of course, what you always see is a dot, right? You see a particle. But if you keep getting many, many, many dots, what you see is that the collection of all of these observed particles show the existence of interference patterns. You get an interference pattern from a wave interfering with itself. There are waves that come through one slit, waves that come through the other slit. Sometimes going up, sometimes they're going down. They can constructively interfere to add together, or they can destructively interfere to cancel each other out. That's what these waves, that's what these interference bands in the pictures are showing us. So this is very direct evidence that the wave function is a real thing. It can interfere with itself. How could it not interfere with itself if it were just a tool that we used to make predictions? So I'm going to go with the wave function being real. The other thing we need to understand is a phenomenon called entanglement. This was named by Schrodinger, but it was really elucidated by Einstein and his collaborators, Podolsky and Rosen, in 1935. But I think I can give you a little motivation for why entanglement makes sense. So consider a particle, a single particle, maybe the Higgs boson. The Higgs boson is a good example because it's a pretty featureless particle and it's unstable. It decays into two particles at once. So when I say featureless, the Higgs boson has no charge, it has no spin, nothing like that. It's the most kind of basic particle you can imagine. and it will very quickly decay. And as we alluded to earlier, when a particle decays, you can use the Schrodinger equation to predict what the wave function of the decay products will be like. So let's imagine the Higgs boson decays into two other particles, particle 1 and particle 2. And you see particle 1 here in green, particle 2 there in red, and they're moving out in a spherical pattern, okay? But there's two things going on. One is that you can observe these particles. You can't predict exactly where you will observe them because they're moving out in a spherical pattern. But if you have a cloud chamber around them, you're basically constantly observing them and you'll get a little track. But if instead you just wait for them to travel a little bit and then observe them, you'll get a dot somewhere. You don't know where the dot will be. You can predict it probabilistically, okay? That's one thing. And the other thing is there's something called conservation of momentum. So let's imagine that we detect particle 1. We use a little eyeball as a representation of you've detected the particle with momentum that way. But the initial Higgs boson, the blue particle on the left, has 0 total momentum. So when you detect the green particle, particle number 1, moving in a certain direction, you instantly know that the red particle had to be moving in the other direction because momentum is conserved. So just by measuring particle 1, even though it could have been everywhere, and particle 2 could have been everywhere, there's a connection between them. Measuring particle 1 instantly tells you where particle 2 was. In other words, the wave function of particle 1 collapses because you measured it. The wave function of particle 2 instantly collapses along with it, whether or not you measure that or not. And then the same thing would happen if you measured particle 1 in some other direction or any of the other possible directions. What is this telling you? It's that this idea that the wave function is used to predict a probability of observing things is not individually particle by particle. The phenomenon of entanglement says that there is only one wave function. It's not that there's a wave function for particle 1 and separately a wave function for particle 2. There's a one wave function, the wave function of the universe, that is dependent on both particle 1 and particle 2. So mathematically, it's not psi 1 of x and psi 2 of x. It's psi of x1 and x2. And in principle, that function of two variables can be anything it wants to be, any complex valued function of those two variables. So there can be hidden connections in the wave function between what you can possibly observe about particle 1 and what you can possibly observe about particle 2. And it's not just for two particles. It's also true for 3 particles, 4 particles, literally the entire world. If you take quantum mechanics at face value, the world doesn't separate into different systems like it does in classical mechanics. The wave function of the universe assigns a complex probability amplitude to every possible configuration of all of the stuff in the universe all at once. That's very different from what we see when we look at the universe, but technically, that's what the apparatus of quantum mechanics is trying to tell you. So to say the same thing in different words, what the wave function is a superposition of possibilities. It's a superposition of different possible measurement outcomes in particular. So the wave function is not a wave of a field propagating in ordinary three-dimensional space. A field, if you've ever heard of like the electric field, the gravitational field, quantum field theory or whatever, the whole point of a field is a function of space and time. That's it. At every point in space and time, the field has a value. The wave function is not a function of space and time. You can get tricked into thinking it is if you're thinking only about one particle at a time. But as soon as you think about two particles or more particles, you realize the wave function is a function of the configuration space of all the particles in the universe, or the configuration space of all the fields in the universe, or whatever you want to make the universe out of, okay? It's a very different thing than the ordinary fields that we were used to from classical mechanics. And so what you should imagine in your head, this is a picture of a chair in a room. Imagine all the possible places that chair could be in the room. The wave function of that room assigns a complex number to every possible place that chair could be in the room. And the answer that quantum mechanics provides is the probability of seeing the chair somewhere is that wave function squared. So again, at face value, without trying too hard, just listening to what quantum mechanics is saying, we seem to be driven to a view of reality that says that quantum mechanical reality is a superposition of all possible configurations of stuff in space. And reality is not just one configuration, it's the superposition of all of them. So the guy to actually take this seriously was Hugh Everett. He was a graduate student at the time. It's graduate student PhD theses that did a lot of the most important work in the foundations of quantum mechanics. Okay. So Everett basically acts as a therapist to the physics community. He says, you folks have just been worrying too much. You've been working too hard. Here's the answer to the reality problem. The wave function represents reality. Exactly. And it's entirely. There's nothing else there. Most importantly, you are part of the wave function. So the founders of quantum mechanics, Bohr, Heisenberg, et cetera, the establishers of the Copenhagen interpretation, were insistent that the observer is classical. The observer is treated by the rules of classical mechanics. The quantum mechanical system is quantum, but the observer is not. So they erected a barrier between the microscopic quantum world and the macroscopic classical world. And that's weird because human beings are made of atoms and atoms are quantum. So at what point does quantum mechanics mysteriously stop applying? So Everett says, I, the observer, am absolutely part of the quantum wave function just like everything else. And what happens in measurement, Everett just says, there's no such thing as measurement. All that ever happens is the wave function obeys the Schrodinger equation. Let's see what that means. So what Everett is saying is, here are the rules we ordinarily taught for quantum mechanics in textbooks. Everett says, I'm going to erase all these rules I don't like. I'm going to erase all the rules that have something to do with measurement. To me, Hugh Everett, quantum mechanics just said systems are described by wave functions, and those wave functions obey the Schrodinger equation. That's it. Now, why isn't this obviously right? This is obviously very simple, very elegant, very austere. Like it satisfies a lot of the good criteria for a good scientific theory. Well, the answer is that at the time, in the 1950s, people would have said it disagrees with the data. And let me explain to you what that means. To do that, we can invoke the thought experiment stylings of Erwin Schrödinger and the famous Schrödinger cat thought experiment. Now, Schrödinger's daughter once pointed out that she thinks her father just didn't like cats. So in the original Schrödinger's cat thought experiment, the cat is put in a superposition of alive and dead. But I am a cat person, so I'm going to put this cat in a superposition of awake and asleep. It's exactly as good for thought experiment purposes. So the idea is we have a radioactive source that's going to give off a decaying particle. There's a Geiger counter that can click if the decay happens. And if it clicks, it opens a little container of gas that fills the box. Otherwise, there's a cat in the box that would be awake. But if the container opens, sleeping gas fills the box and the cat goes to sleep. So the point of this elaborate Rube Goldberg device is to take the quantum mechanical superposition of the decaying particle, which is a superposition of I have decayed and I have not decayed, and turn it into a superposition of a macroscopic creature, namely the cat, okay? So basically, Schrödinger is just trying to say, I can follow the rules of quantum mechanics, the equation that I wrote down, and I can amplify the superposition from a microscopic thing to a macroscopic thing. And by the way, he didn't think this happened. He was saying, these are your rules of quantum mechanics. These are not mine. I just invented the equation. But if I take them seriously, this is what I get. Surely you don't believe this. And just to drive home the conceptual shift here, classically, it's completely possible that in the box there's a cat. The cat may be awake or may be asleep. We just don't know, okay? That is classical uncertainty. Quantum mechanics is saying something different. It's saying that the real physical reality could be a superposition of both at once, at least until you open the box and look at it and the wave function collapses. So I'm using notation here where the square brackets are for classical concepts and the ordinary parentheses are for quantum mechanical concepts. So classically, the cat is one or the other, even if you don't know. Quantum mechanically, it can be a superposition of both. So here is how you would talk about Schrodinger's cat in the Copenhagen interpretation. You would say that the cat, according to the rules, is in a quantum superposition of awake and asleep. And there's an observer that is classical. The observer in this picture is played by Niels Bohr. And what's going to happen is Niels Bohr is going to open the box, look at the cat, the wave function will collapse, and you will either get a situation where the cat's awake and the observer saw the cat awake, or the cat's asleep and the observer saw the cat asleep. That is the textbook version of quantum mechanics. Now, contrast that with Everett's version. What Everett says is you have to treat the observer as quantum mechanical as well. The observer is part of the wave function of the universe. So you have a quantum state that is the cat's in a superposition and the observer is ready to observe. And then the measurement process is simply obeying the Schrodinger equation and the observer becoming entangled with the cat. So the wave function doesn't collapse. It's always obeying the Schrodinger equation. And what happens is you get a superposition of the cat's awake and the observer saw it awake, plus the cat's asleep and the observer saw it asleep, okay? Everyone agrees, everyone who knows quantum mechanics agrees that this is the prediction of the Schrodinger equation. What they disagree about is whether this is what actually happens in reality. The reason why they disagree is because there's a puzzle here. If you just believe that, it seems to be suggesting that when I do a quantum mechanical measurement, I myself, the experimental physicist, enter a superposition state. This seems to be a description of a superposition of an observer who saw the cat awake and an observer who saw the cat asleep. But in reality, every time an experimenter does an experiment, they see a definite outcome. No one has ever felt like they're in a superposition of seeing the cat awake and seeing the cat asleep. Real experimenters always ever see one or the other. So keep that puzzle in mind, and I will add one more ingredient. The other ingredient is this idea called decoherence. Remember, I've been telling you that the point of quantum mechanics is that there is only one wave function for the entire universe. And then I tell you a story about a cat and an observer. Well, what about the rest of the universe, right? In principle, you should keep it in there. And again, here's where we're going to get a crucial distinction between classical mechanics and quantum mechanics. In classical mechanics, I can ignore the rest of the universe. As long as it's far away or not bumping into me very violently, I can turn its interactions to be negligible and ignore them. Quantum mechanics doesn't let me do that. That's what decoherence is about. So we're going to take the entire rest of the universe and bundle it up into something we call the environment. It's represented here by some leaves of grass. And that includes, for example, the air in the room that you're breathing right now. It includes the photons, the light particles in the room that you're seeing with right now. So if you have a cat that is in a superposition of awake and asleep, the awake cat is walking around trying to get outside the box. The sleep cat is lying on the ground, on the floor of the box. The environment interacts with those two versions of the cat differently. There are photons that will hit the cat and be absorbed by its fur if it's awake, but entirely miss the cat if it's asleep. So what happens is very, very rapidly, the environment becomes entangled with the cat. So long before the observer opens the box, the wave function of the combined cat plus environment system becomes an entangled superposition. And then when the observer goes to do the measurement, you break up into two pieces. One piece is cat's awake, environment monitor the cat to be awake, observer observe the cat to be awake. The other part is cat's asleep, environment monitor the cat to be asleep, observer saw the cat asleep. So hold that in your mind. We're going to repeat it on the next slide right here. And now you stare at this and you ask, what is going on? Okay, this is again just the prediction of the Schrodinger equation without any extra ingredients added. And what Everett says is the mistake you were making before is identifying yourself in the wave function. It looks when you write down that wave function as if there's an observer who is seeing the cat awake, an observer who's seeing the cat asleep, and you think, but I don't ever feel like I'm in a superposition of that. And Everett says you're not in a superposition of that. You are one or the other. There are now two observers. there's an observer who saw the cat awake and an observer who saw the cat asleep. And again, it's just because of the prediction of the Schrodinger equation. Nothing more was ever put in. And the reason why that makes sense in the modern way of saying it is that these two branches of the wave function have decohered from each other. They are so different because of the environment interacting with the cat in different ways that nothing that ever happens in one part of that wave function will have any effect physically on what happens in the other part of the wave function. It is as if they have separated out and become separate worlds. So Everett does not invent his new way of thinking about quantum mechanics by putting in a bunch of worlds. The worlds were always there in the space of all possible wave functions. Everett points to the fact that the Schrodinger equation brings these worlds to life, and all he says is, and that's okay. We should just understand what's going on, and we can recover all the ordinary successes of quantum mechanics. So not everyone agrees with Everett's point of view on this. They have objections. Some of these objections are good ones. Others are less good. Let's run through some of the objections. One of the objections is just that there's too many universes. I don't like it. You don't need to go to all this effort to build a device with a cat, et cetera, to split the universe into multiple branches. Every time a nucleus decays, it could be in a superposition of decayed and not decayed. And even if you don't explicitly notice it, the universe will branch. And in your body, roughly speaking, there are about 5,000 radioactive decays per second. So the universe is branching all the time in Everettian quantum mechanics. And in the formalism of quantum mechanics, there's plenty of room for all of those universes. It doesn't matter. So the point is, Everett doesn't put in more universes. If you believe that an electron can be in a superposition of one... Did I freeze?
We have a question.
Oh, there's a question. Okay, that's okay.
I'm just wondering if on the previous slide, when you say decoherence, should I think of this as being a mixed state now?
No, the universe as a whole is in a pure state if it starts in a pure state. If it started in a mixed state, it would evolve to a mixed state. But the point here is that you are always evolving according to the Schrodinger equation. As long as you keep the whole picture, cat, environment, observer, that system evolves unitarily, as we say in quantum mechanics, and a pure state will evolve to a pure state. You can, if you want, ignore some of the universe. Ignoring the environment is a very traditional thing to do. And then the rest of the system will evolve into a mixed state. That is true. But if you kept the environment along, then everything is still pure.
So how do we know that the distinct branches will never affect each other if you could apply some unitary where, the result of that depends on both branches?
Well, we know what unitary you actually do apply, namely the Hamiltonian time evolution operator, e to the minus I ht, right? And the point is that these two environment states, the one with that is monitor the cat being awake and the one that is monitor the cat being asleep, are orthogonal in Hilbert space. Now, that's not obvious, but you can prove it. You can prove that they very, 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 very quickly, like 10 to the minus 20 seconds is a typical time scale for decoherence. They evolve to be essentially orthogonal to each other, and they stay orthogonal to each other on a time scale much longer than the current age of the universe.
I see. Okay, thank you.
Sure. More questions while we're paused? I think there are people in the class who know more than I was told that they would know, but that's okay. That's perfectly allowed. All right. As I was saying, if you are willing to believe that an electron can be in a superposition of being one place or the other place, or it's in a superposition of spinning clockwise or spinning counterclockwise, then you've already done the hard work. You should be able to believe that multiple particles can be in superpositions, and you should be able to believe that the universe can be in a superposition. It's not any harder to have the universe be in a superposition than a single electron being a superposition. Being a superposition isn't like lifting a heavy weight, okay? So all those superpositions are already there in the space of quantum possibilities. The second argument is that this can't be tested, right? because you can't see the other worlds. This is a classic philosophy of science mistake. The idea of what makes a respectable scientific theory should never be that your theory makes predictions that can't be tested. The idea should be, does it make any predictions that can be tested? And indeed, are there predictions which if I observe them one way rather than the other way, would falsify my theory? And remember, the Everett interpretation simply says a system always obeys the Schrodinger equation, even if it is left undisturbed, even if it is not being measured or decohered or anything like that, it will simply obey the Schrodinger equation. There are alternative theories of quantum mechanics where the system does not always obey the Schrodinger equation, and there are experimental tests looking for those effects. They haven't found any yet. I don't think they will, because I think Everett was right. But if they ever found the spontaneous collapse of the wave function, that would instantly falsify the Everett version of quantum mechanics. It is the most falsifiable theory that you can imagine inventing in the sense of quantum mechanics. Another not very good objection is, where does the energy come from for all these worlds? So if I'm really literally imagining the entire universe around me splits every time I measure a quantum system into multiple copies of itself, that sounds like I'm making a lot of universes, and don't universes cost energy? And the answer is no, they don't. Or at least the wave function of the universe has a certain amount of energy in the simplest way of looking at it. I mean, we're getting into deep questions of quantum gravity and quantum cosmology and things like that. But if you just forget about gravity and do ordinary dumb old quantum mechanics, the wave function has a certain Hamiltonian, as we say, and you could calculate its expectation value. And that's conserved over time. As long as the whole universe obeys the Schrodinger equation, energy is exactly conserved. Now, the reason why it doesn't look like it's conserved is because the universe you're in gets thinner. So this diagram is a picture of the universe branching from bottom to top, and this the branching because of various events that are described by interactions and entanglement and decoherence. And for each branch, there's a value of the wave function. You can square it, and that's where you get the thickness, the weight of the branch. And there is a conservation rule that the sum of the thicknesses of all these branches stays constant. And the expectation value of the Hamiltonian, what you would call the energy of the entire system, is weighted by that weight of the branch. So when you're inside a world, the weight of your branch is getting thinner and thinner, but that includes you. So you, relative to the sun and the earth and the moon and the stars, etc., have the same energy you always did. That's why it looks like energy is essentially conserved. Now, notice that the different branches don't need to have exactly the same energy. The whole shebang has a constant energy, but you can have wave function branching events where more energy ends up in one branch than the other one does. Everett says that's fine. The whole multiverse is all of these branches at once. But the Copenhagen interpretation says, no, 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 you only get one measurement outcome. So in the Copenhagen interpretation, energy is not conserved. In the Everett interpretation, energy is conserved. If you have some romantic attachment to the concept of energy conservation, Everett is a much better theory than Copenhagen is. And finally, on a more sort of psychological aspect, people do worry about the idea that there are other versions of themselves out there in the multiverse. They think of themselves as having continuity through time. You're born as a baby, you grow up, etc. You have a self. You have a selfhood that is personal identity in a very important way to you. Now, am I supposed to think of versions of me on other branches of the wave function as also me? That disturbs me somehow. But the answer is no. Those people on other branches of the wave function might have shared a past with you, but they are not you. Once that branching happens, once they're now separate universes, they have gone their separate ways, and those people are different. It is exactly like identical twins. Identical twins start out as the same fertilized egg, one entity, but at some point it splits into two people. And when you have two identical twins, you don't think of them as two parts of the same individual person. You don't think, well, if one twin dies, it's no big deal. We have a spare part of the twin over here. These are two different people. They deserve rights and dignity each individually by themselves. So when it comes to things like ethics and morality and how you should behave, it's exactly the same in many worlds as it would be in a single world with probabilistic wave function collapses. Don't have time to go into too much of this, but very quickly, I will mention that there are also good unanswered questions for many worlds, or at least ones where the answers aren't agreed on. And I'll mention two of them. One is, why are the probabilities for different measurement outcomes given by the square of the wave function? In Copenhagen, you can literally be a good old-fashioned frequentist, right? You can do the same experiment over and over again and say the frequency of certain outcomes is given by the Born rule. In Everett, in a very direct sense, every possible measurement outcome happens with probability 1. It just doesn't happen on the same branch of the wave function. So where do probabilities come in at all? The theory is deterministic. And the other question is, how do you get a classical world at all? Why does the world look so classical if the only thing going on is the Schrodinger equation? This is what I would talk about in an ordinary physics colloquium version of this story, but here I'll just give you two slides. One slide is saying that the answer to the probability question is to say that even though the wave function is an objective physically real thing, probability is epistemic. Probability is subjective. You can know exactly the wave function of the universe, but there's something you don't know, which is where you are within it. That is called self-locating uncertainty. So think about that evolution of the cat, the environment, and the observer in the decoherence step. In this step where decoherence has occurred, there's a moment where both of the observers haven't yet looked at the cat. And you can argue that this moment is more or less inevitable. So there are already two branches of the wave function because the branching happens when the environment becomes entangled with the system. But the two copies of the observer are identical on these two branches of the wave function. So how do they know which branch they're on? The answer is they have to accept that uncertainty and assign a credence to it. And you can argue what credence should they assign, and the sensible, rational thing to do is to use the Born rule to assign credences. So there is an origin for probability, but it's fundamentally subjective rather than objective. The other issue is, where does the classical world come from? I'm not going to get into that. All I will say is, this is a good challenge for Everettians to start with pure quantum mechanics, not using any pre-existing classical notions, and show how the classical world emerges naturally. This is something that I myself have as a big part of my research program. I think you can see it happening, but we're a long way from completely knowing the answer to that. So this is a fun little bit of unsolved question. But the motto of it is time to climb outside of the box of the classical world and accept quantum mechanical reality for what it is. Thank you very much.
Hello, thank you for the presentation. So I had a question. So you said that like the world is like branching off and there are many separate worlds that never interact, but is it the same? You could say that it's the same or different if you consider like the worlds with separate entities to begin with that just happen to be identical, and then that them as branching is just an optimization of like, it's easier to do the math that way. Is that a possible interpretation?
It is 100% a possible interpretation. Yeah, this is a very, very good point. So the usual way of talking about branches in Everett is there's one branch to start, and over time, as decoherence happens, you get more and more. But an important aspect of branching is that it is a human construct. The wave function is objective, but how we divide it up into branches is something we do for our convenience. Laplace's quantum demon doesn't know about branches. It just knows about the wave function obeying the Schrodinger equation. So it is convenient to us to talk this way, but you could also imagine letting the clock run, letting evolution happen, branching the universe into all of its copies, and then sort of extrapolating all those eventual copies backward in time and saying they were always just many copies, even though they looked identical to each other. There's a good philosophy question there as to how respectable that is. Does that work all the way through? Can you really, is it sensible? Is it well defined to split up the world in branches, even if they're identical? And I haven't really thought about that very much. So I'm open to the possibility, but I don't see the need for it, except insofar as it helps reconcile you to the probability question. You always were one of several different observers. You just didn't know which one you were.
Right. Yeah. Okay. That makes sense. Kind of.
Yeah.
Thank you.
Sure.
Well,
So actually, people, I actually, at the risk of asking a technical scientific question. So did I see correctly that the paper that you're referring to about this epistemic nature of probabilities being consistent with the Bohr rules, that something you wrote with Stebbins? Is that the
Sebens, Chip Sebens is a philosopher now at Caltech. Yeah, he was a grad student at Michigan at the time that we wrote the paper together.
I see. So yeah, maybe I won't ask you more about that right now. I'll go and read it and find out, because I mean, as you know, there are lots of different approaches to trying to get the Bohr rule by lots of people, including ones by you, by me, by like Jim Hartle, and lots of people, but nobody's ever really kind of like gotten a really good handle on it. So I guess, yeah, maybe a question about that, since I don't know the paper, is does it really require you to have the Bohr rule, which is rather an odd thing, that probability goes the square of the amplitude of the wave function? Because that's what seems to be rather hard. I mean, it makes some kind of sense. It's some function of the amplitude for when you have a branching event, that it's some function of the amplitude for the things, but getting it to be the Bohr rule seems to be difficult.
I think that's, to me, that's not the hard part. In fact, I would have said almost exactly the opposite, Seth, of what you just said. I think that once you think that there is a probability distribution that you should use to assign credences as to what branch you're on, it has to be the wave function squared. Oh my goodness, what else could it be? The wave function squared is a set of numbers between 0 and 1 that add up to 1. And they always add up to 1, even as the universe evolves with time. It's not going to be the wave function cubed. It's not going to be the log of the wave function, right? It's literally Pythagoras's theorem. That's where the square comes from.
Okay, because I mean, in the original paper by Born, he originally said it's probability is proportional to the amplitude, not the amplitude squared. And then he got the Nobel Prize for putting in a footnote added in proof, saying, oh, gee, footnote added in proof, I realized the probability goes as a wave function squared, not just the amplitude for it.
There's a non-zero chance that you first heard that from me, because yes, I've said that in talks that I've given. I've shown the footnote.
Oh no, I think I heard it from Wojtek Zurich a long time ago.
Okay. It is very funny, but of course it couldn't be the wave function. That's a complex number it can be negative. So
right.
Yeah. So let me actually add one thing to that. There are, like you said, there are many attempts to derive the Born rule within many worlds in particular.
Right.
Within the foundations of physics community, many of these attempts are sneered at because they secretly assume the answer. They secretly beg the question one time, one way or another, including Everett himself. There's a history of ways of quote unquote deriving the Born rule that try to put a measure on the space of all the branches and then argue that branches on which the Born rule is not obeyed are a set of measure 0. And we're in the limit as the universe gets older and older. And then, of course, we assign 0 probability to a set of measure 0. But that last, of course, is doing all of the work. And also the existence of a limit is doing all the work where the limit might not exist. So I think that our derivation is a little bit more robust, but it's also more sort of philosophical in character.
Great. I will read it, and then I will send you some questions.
Yeah, please.
I think your point about Everettianism satisfying conservation of energy is really a powerful one and an important one, and not really understood in pedagogy. So that was I appreciate you framing that. Also appreciate the point about Bell's inequality, that he he didn't quite do that, which most people don't know about at all.
Right.
I know some of these types who, and then, but they don't conclude, they know what you mentioned, but also just don't believe in Everettian. This notion that we are, in some sense, I feel like we're a little bit reifying, what is a U and a wave function anyway, right? What does it mean to be U? And we're reifying ourselves, and that feels problematic. And I think that there's probably still a little more commentary to be done on what Bell actually said, so we all get on the same. I mean, there feels like, a Teutonic and an Anglo tradition, and they're different things, and nobody's even up to date on what happened there in the philosophy of science. So thank you for pointing that out.
Sure. Actually, if I can beg your indulgence to say one more thing about energy conservation. It was I was inspired by these tests of alternatives to many worlds, like spontaneous collapse theories. In something like what is called the GRW theory, where a wave function has a probability per unit time of spontaneously collapsing, that very obviously and manifestly violates energy conservation. And indeed, that is how they're doing the experimental tests. You put something maybe like a super cooled superfluid kind of thing, a Bose-Einstein condensate, and if there's enough atoms in there and you wait long enough, one of them will spontaneously collapse its wave function, and the whole thing will go out of the supercooled state, right? So if that's okay, I started wondering about regular quantum mechanics. And the Jackie Laudman, who was a undergrad at the time at Caltech, who is now a grad student at Harvard, she and I wrote a paper pointing out something that is it's one of those things where, well, we point out in the process of quantum measurement, not in the unitary wave function of the evolution, but in the measurement process, if you define energy as the expectation value of the Hamiltonian, that is clearly not conserved when you make a quantum measurement. And if you tell a physicist on the street this, they will say, sure, but that's because the energy goes into the environment or the apparatus or whatever. So you can straightforwardly prove that's false. You can easily make examples where it clearly doesn't. The different observational outcomes have different energies in their branches. So we wrote a paper and we submitted it. And of course, we do exactly what would happen. One referee says, this is so obvious, why did you bother to write a paper about it? And the other says, this is so obviously wrong, you should be embarrassed to think it's true. And then the journal rejects it. So, we got into a different journal, but it is very difficult to get people to think consistently about quantum mechanics.
Indeed. There's another question. We'll get out of the seat.
I don't know that this is going to be phrased right, but with the branching, in order for it to work, don't you have to assign different weights to each branch, and only some of the normal branches would follow like classical quantum mechanics in terms of Born rule in the physics? And so you'd have to currently be existing in one of the normal branches. So isn't this dependent on like the low odds that the branch we are occupying is one of those normal ones that obeys the classical laws of physics?
By normal, do you mean has the statistics of the Born rule in it? Yeah, so like I could do something like set up the measurement of a quantum spin, and I could set it up in a state where there's a 50-50 chance for it to be spin up and spin down. and I could do that to 1,000 spins, right? And so I would get 2 to the power 1,000 branches of the wave function of the universe. And in every one of them, it would be a different series of outcomes, up, down, 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 up, down, etc. Right? And you can show, people like Seth Lloyd have shown, and others, that on the large majority of those branches, the statistics will be approximately 50-50, spin up and spin down. Just because there are so many more branches where it's approximately 50-50, just due to like law of large numbers kinds of things. So you actually don't need to worry about if you believe ever-ready quantum mechanics at all, you should weight your expectations by the weight of the wave function, and then everything, the probability of seeing something weird is just the same probability of seeing something weird you always would have expected in quantum mechanics.
But if majority of those obey like what you'd expect in terms of 50-50, then there's some that don't. And if
There absolutely are, yes. So too bad.
but if you were occupying that branch that doesn't act as expected in in typical physics, then those worlds would, as if if you were in one of those worlds, multiverse would not work quite right. Like you wouldn't be aware of the other paths because the physics would be completely different.
That's right. And it would suck to be you. But many, 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 many more worlds have the typical expected behavior.
But then you're going that this theory works because chance we're in one of the normal branches.
Yeah, because it is overwhelmingly probable that that's what things look like. This is very, very similar to the controversies about statistical mechanics in the 1870s. You know, in the mid 1800s, people had thought of something called the second law of thermodynamics. Entropy increases. It's a law of nature. And then Boltzmann comes along and says, actually, it's just really probable because there's a lot of particles in your box. And people were outraged by this. They said, what do you mean really probable? Like, I want it to be a law. And he says, well, but it's really, really, really probable. And that's how it is in quantum mechanics. Yeah, the only difference is that for Everett, there will be some unlucky individuals. There are far, far, far fewer of them, but a few individuals are going to get the laws of physics wrong. Yeah.
Okay, then say we're in one of those branches where the laws are wrong and we're looking for theories from that branch.
Yeah,
It's
we'll
not-
be wrong. We'll be unable to get the right answer. Happily, that is very, very unlikely to be true.
Yeah, but not 0 then.
Not
So-
0. Yep.
Okay, thank you.
I mean, as soon as you go back to the table and put your computer on the table, according to quantum mechanics, there's a non-zero probability the computer will tunnel through the table and crash onto the floor. Happily, it is very, very unlikely.
Yeah, can you come in front to the, we have another question.
So within this many world theory, is there any kind of time reversal symmetry? I mean, does this theory guarantees time reversal for quantum mechanics?
Right. So again, there's a very close analogy. In fact, it's kind of more than an analogy between ever-ready quantum mechanics and statistical mechanics. In the following sense, the dynamical rule that is relevant is completely time reversal invariant. It has no distinction between past and future. The Schrödinger equation does not distinguish between past and future. Just like in statistical mechanics, Newton's laws of F equals ma do not distinguish between past and future. But you get a direction of time by imposing a very special boundary condition in the past. In statistical mechanics, the boundary condition is that the universe started with low entropy. In quantum mechanics, is that the universe started in a single branch. And that initial condition of the wave function gets you everything you need in terms of the future time asymmetry.
So in classical statistical mechanics, we have something like entropy, which we can measure it and know the time. So is it any similar thing in this many worlds theory, like entropy?
It's a similar thing. Like that's why I hesitated a little bit to say that it's analogous, and I would argue it's the same thing because the real world has both quantum mechanics and statistical mechanics, right? And there is a unified framework, that people like David Wallace have talked about, but I still think there's some work to be done in completely sketching it out. But you need to explain things like, why do I think I have records of the past, but I don't have records of the future? Right. And I think that is going to come in the same words that you use to answer that question in the context of statistical mechanics, you will also use to answer that question in the context of quantum mechanics in Everett. Yeah. Whereas, by the way, in the Copenhagen interpretation, it's just put in by hand. Wave functions collapse toward the future. They do not anti-collapse toward the past. So that's another way in which, you might be slightly unsatisfied with the Everettian explanation, but it's clearly better than the textbook explanation.
I see. Oh, thank you.
Yeah, please. More questions coming up.
Troublemaker is back.
Yep. Why not towards the past? Your point was that it's not going toward, okay. This thing said prior was that the wave can't go backwards, but if it was going between going forward and going backward, like two waves collapsing agreement, that would account for the same thing as the branching would.
There's a separate set of words to say in conventional quantum mechanics and in many worlds. In conventional quantum mechanics, again, imagine I have a spin that is in some superposition of spin up and spin down. And I measure it and I get spin up. And the usual story says, I can predict the probability. I can't predict actually what I will see, but I can predict the probability of a measurement outcome based on the wave function squared. But conventional quantum mechanics also says, if I tell you I have already done the measurement and I got spin up, but I don't tell you what the original wave function was, you cannot figure out what the original wave function was. You cannot retrodict from the current state of the system to the previous state of the system. There are many, many, many initial wave functions that had a probability of giving you spin up at the end of the day. And in conventional quantum mechanics, you just say, that's just the way it is. You got to deal with that. In Everett, you say, well, we're hypothesizing that the universe starts in a special state, that there is only one branch with relatively little entanglement between what we call systems and what we call the environment. And as time goes on, there's more and more entanglement. And so you could, in principle, retrodict by conditionalizing on the initial state that you started with. It's a little bit more of a complicated procedure, but you're basically being a little bit more honest about what you need to put in. The dynamical equations, once again, are entirely reversible.
But this theory accounts for it by as many branches as possible, just no necessary mechanism for splitting, but it keeps going out. It's like no bound on the theory. If you do it forward and backward in time, then it's like a nice little loop. That's where the information is coming from. It would explain why we don't have the information that accounts for the collapse in the outcome. And
well, there is, so I'm not sure if what you're putting your finger on is this, but I'll just, my strategy is to say things I think are true, and then you can tell me whether they're helping you with the question or not. There's an obvious shortcoming in this picture. I don't know, can you see the pictures on the screen still? Yeah, there's an obvious shortcoming here in that there is a beginning and an end to the evolution, right? There's a first moment in which I plot the figure and a last moment in which I plot the figure. The Schrödinger equation has no beginning or end, right? You can just run time forever. And in principle, if there's a technicality that comes in, is the space of all possible wave functions, which is called Hilbert space and is a vector space. Is it a finite dimensional vector space or an infinite dimensional vector space? We don't know for the real world. There's arguments on either side. If it's a finite dimensional vector space, then something very much like what you just said happens. A finite dimensional vector space means there's not an infinite number of vectors you could possibly go to. So the Schrodinger equation will eventually bring you back to whatever initial condition you started with. There's a theorem, the quantum recurrence theorem, that says exactly that. There's all sorts of reasons to hope that is not the real world. An eternally recurring quantum universe would raise other issues with Boltzmann brains and things like that. I don't know if you were given the possible readings, but Boltzmann brains are things that can fluctuate out of the nothingness. They're bad. You don't want them. In an eternally existing, recurring quantum universe, you would expect that most copies of you are really Boltzmann brains, and that would be bad. So if the other option is that Hilbert space is infinite dimensional, and then you never have to recur, then the recurrence time is infinity, then this wave function can just branch and branch and branch forever, and it'll get sort of more subtle as time goes on, but it will never have to come back to where it started.
But that's taking it and applying it to the entire theory of like many worlds interpretation, that like from start to end of however many branches. But I'm saying like at one individual branch, when it starts to branch, you're accounting for the arrangement of the equation as like both outcomes end up happening. But instead, if the wave is like a wave going forward and a wave going backward in time, wouldn't it have the same effect in terms of it accounts for the math?
I'm not sure what it means to have a wave going forward and a wave going backward in time.
Okay.
There is here, Sean, there are theories of quantum mechanics where the wave function collapses into the past, because it's got to be possible to do that because the equations of motion are different. And then there's so it seems sort of strange, it's not a Copenhagen interpretation, but it gives the same probabilities for sequence of events, so can't distinguish between that. And then there's another interpretation called the transactional interpretation, and it was kind of like a wave going forward, you know, from one collapse event, goes forward to one collapse event and meets up with another wave going backwards from another collapse event, and they kind of duke it out, like see how it happens. It also gives the same probabilities for sequences of events though. So these different ways of describing this are just, you know, artifacts of how we choose to describe it. But you can definitely describe it in a time symmetric way if you choose to do so. This is kind of impressionistic. I could show the math for this, you know, sometime next week or something like that.
Thank you.
All right, thank you, Sean. I had questions about CTDs, but it feels like a very different talk. So I hope, but we'd be grateful if you came back for another hour to talk about the energy restrictions on GOT time machines paper.
We can do that. It's a totally different thing, but I'm very happy to talk about it.
Exactly. Okay. Well, thank you very much for this talk.
All right.
Appreciate it.
Okay. Thanks, everyone.